In our third and final video for chapter 20, we're going to look at a bunch of other functional groups. And the idea of what a functional group is was introduced in video 2. It kind of controls the reactivity of a molecule. We'll talk about how these functional groups react, but a large point of emphasis for this chapter will knowing what these functional groups are, right, and how to identify them. For example, we start with alcohols. And everything we'll see today is a derivative of a hydrocarbon, right? We've added some other substituents on there. So an alcohol is a derivative of a hydrocarbon where one of our H's has been replaced by an OH. Okay? So that's one of the things you'll look for in an alcohol, okay, an OH group. It's not the only thing because that can also be present in a carboxylic acid. Okay? So we've got an OH group. Everything's covalently bonded, right? And that OH group shouldn't throw you off. Okay? We talked about that in chapter 4 when we first introduced the idea of bases. If you see an OH with a metal, then that's typically going to be a strong base, like sodium hydroxide. Okay, but this OH covalently bonded to carbon, right? So these guys aren't acting as bases. If anything, they're very slightly acidic, okay? But they can participate in hydrogen bonding. We saw that all the way back in chapter 10. We name an alcohol by replacing the E at the end of the name of the alkane with OL. And then we add a number to indicate the position. Right? So ethane, we drop the E and it becomes ethanol. That's also done in fermentation, right? Glucose goes to ethanol via yeast. We see that OH, it's an indication we have an alcohol. Can also prepare them from alkenes. Okay? It's known as a hydration reaction. Right? Water adds to an alkene, and we get, again, an alcohol. Be able to identify those. We can have one OH in a molecule. We can have several OHs in a molecule. And these things aren't just alcohols like rubbing alcohol and the alcohol that you drink, right? Ethane diol over here is antifreeze. Propane triol, glycerin, which is used in medications. So know that OH means an alcohol. Next functional group, an ether. That contains the functional group ROR. And R is a general term, kind of like the things we've used in the past. Like I've used X to represent a halogen. R is just a general symbol for an alkyl group. Okay? And it could be a methyl, a propyl, anything. Really, it could be two different things. But it doesn't change the identification of the functional group. So if you see a carbon single bonded to an oxygen, that oxygen's again single bonded to a different carbon, that's an ether. Right. Here's an example of an ether. This is diethyl ether, which was an original anesthetic. And naming these guys in the IUPAC system is a little more complex, so we're not going to test that in this chapter. You would be responsible for it if you take organic. We can also prepare ethers from alcohols. This is known as a dehydration reaction. Two alcohols coming together to form an ether. Right? See that COC, ether. Okay. Now what to be on the lookout for is a C double bond O, which is known as a carbonyl. Okay? Because if that's next to an OH or an OC, that would change the name of the alcohol or the ether to something else. We're going to start by considering aldehydes and ketones. Okay, we'll see pictures of those next. Okay, but the nomenclature is down here. To name an aldehyde, we cut the E off of the end and add AL. Notice it was OL for an alcohol, AL for an aldehyde. And for a ketone, we drop the E and add ONE, O-N-E. And here's two examples of a ketone and an aldehyde. If you see that carbonyl flanked by carbons on each side, that's known as a ketone. Right? Remember, R is representing the alkyl group. If you see a carbon on one side of the carbonyl and a hydrogen on the other, that's an aldehyde. Okay? So be able to identify those. Here, we see a C double bond O and an H, that's an aldehyde. Here we see a C double bond O in the middle of two C's, that's a ketone. These are the symbols to show how they're represented in condensed formulas, like if we're writing a formula on the line. Right? CHO indicates an aldehyde, and an O in parentheses indicates a carbonyl. Okay. These have their own classes of reactivity. Okay, because of that sp2 hybridized carbon in the middle. And the polar carbon-oxygen bond, which puts a large partial positive on that carbon, makes it act as something that's known as an electrophile in organic. So they have their own classes of reactivity, aldehydes and ketones. But we can make both of them by the oxidation of an alcohol. Here's the general formula of an aldehyde or a ketone, that partial positive I was just talking about. sp2 hybridized, meaning 120-degree bond angle. Oxidation of the alcohols, right? If I take an alcohol here, undergoes an oxidation, it can make a carbonyl. So depending on what was surrounding that original carbon, that can become an aldehyde if it's on the end of a molecule, or it can become a ketone if it was in the middle. Two other functional groups that have that carbonyl, C double bond O, are carboxylic acids, that's missing from the title up here, and esters. Okay. Carboxylic acids have the C double bond O and then an OH, and esters have a C double bond O and then an OR. Okay. So that's what I was alluding to before. An OH on its own is an alcohol, but if that OH is next to a carbonyl, it's a carboxylic acid. And here we see some examples of those. Okay, so we have, if I take isobutyl formate here, and you see all the names because these are used as flavorings, carbon, oxygen, carbon, that's originally an ether. We just talked about that a minute ago. But if one of those carbons also has a double bond O, now it's an ester. Okay. So there's the general formula for an ester. And over here, I see a carboxylic acid. Okay. See, one of them is going to an OH, another bond is going directly to a carbonyl. And those carboxylic acids are so named because they have an acidic hydrogen. Right? This hydrogen right here is a weak acid. That's something we discussed in chapter 14. There's a bunch of hydrogens on ethanoic acid, but only one of them is an ionizable hydrogen that we discussed in 14. This hydrogen on the end is the one that we lose because when those electrons kick back, they're stable due to electron delocalization. Okay? So they have the special reactivity because of that acidic hydrogen. Right? Here I see a neutralization reaction between propionic acid and sodium hydroxide. Esters and carboxylic acids can be made from alcohols as well if you oxidize them further, right? We just saw a second ago, one oxidation can take it to an aldehyde, but you can oxidize it even further to a carboxylic acid. Okay? Do the same thing for esters. Those, you don't have to know the reactions, you do need to know how to identify the functional groups. Our last two types of functional groups are things that contain nitrogen. We'll have amines and then amides. Amines are molecules that contain a carbon-nitrogen single bond. That nitrogen has a lone pair and then is bonded to 3 total groups. Okay, so if we're considering one of those to be the CN bond, that should be 2 other groups. So you've got nitrogen with a lone pair and then 3 total bonds going to either carbon or hydrogen. And those, right, because of the lone pair on nitrogen, those are Lewis bases. They're weak bases, like ammonia, right? NH3 is the simplest amine. We've covered that before, acting as a base. Right? You can also see nitrogen participate in aromatic compounds from the previous video. Those things are known as heterocycles, right? Here's a heterocycle, for example. It's aromatic, but it's not all carbon in the middle, in the ring. Yep. And here's some examples, some amines, right? 3 total bonds to nitrogen plus the lone pair. They can be to carbon or hydrogen. Those amines, as we said, are bases, so they can pick up a proton. We've done that in the past. But if you have an amine next to a carbonyl, that's known as an amide. Okay, so an amide here contains nitrogen bonded to the carbon that also has a carbonyl. Those are made when you have carboxylic acid react with amines or ammonia. And that's unique because that's how amino acids come together in your proteins. Right? And bond characteristics we'll talk about in organic are the reasons why we form structures like alpha helices or beta structures, right, that are covered in biology and biochemistry. So over here, this is an amide, right? Notice the nitrogen going to a carbon that has a carbonyl. This is an amide. This is an amide. Doesn't matter if these things are carbon or hydrogen, you're looking for that C double bond O and CN all together. That's the clue that you have in amide. And this shows how those two come together to link in your amino acids. Okay, shown there, in there via a condensation reaction, which is responsible for the structure I just mentioned. So that concludes our list of functional groups. This is in a table. The quality is really bad here, right? But this is pulled from your textbook at the end of chapter 20. There's a table there that has the name of the compound, the functional group, right, an example, and how to work with it in nomenclature. That's going to be a huge help in terms of a study guide, because you will be asked how to identify functional groups, right? Given this functional group present, what is its name, right? What functional groups are present in a molecule? So be familiar with all the ones that were discussed in this video, plus alkanes, alkenes, alkynes, and aromatics that were discussed in video 2. And that concludes the key ideas from chapter 20.